right. I think this is day 3. Yep, limits and derivatives, day 3. Let's go. I don't know what that is. Let's keep moving. You can look at that on your own time. That one too. Okay, cool. Questions on? Let's pause the video or pause the recording. Do we have just because it's a fun one. Jacob, I can rewrite. Of course, if I plug 0 in here, I'm going to get 0 times 0, or no, excuse me. Yeah, 0 times cotangent of 0. Oh, that's undefined. So I get 0 times an undefined value. So what I'm going to do is I'm going to simplify by rewriting cotangent of x as cosine x over sine x. And if I rearrange, this should become very familiar to you. And if I take the limit as x goes to 0 of x over sine x, what does that go to? 1, right? And if I plug a 0 in here and cosine of 0 equals what? 1. So I get 1 times 1, which equals 1. Anything trig related, typically I try to get in terms of sine and cosine, and sine x over x shows up most of the time. Okay. What is it? Right? A function is differentiable if the derivative as you approach a certain point from the left and from the right are equal. So let's talk a little bit about counterexamples to that, right? Let's say I want to know if this function is differentiable at x equals 2. Well, can we say that the derivative or the slope of the curve at this point looks to be the same coming from the left and from the right? Well, would you agree that the derivative as I approach from both sides looks to be the same? Right? So let's talk about counterexamples. What functions typically would we say have a discontinent or a spot where it's not differentiable? Tangent? Okay, sure, yeah, tangent graph. Why is it not differentiable at a certain point? Because it's not continuous everywhere. In order for something to be differentiable, it has to be continuous everywhere. So let's think of functions that are continuous everywhere but are not differentiable. Absolute value, thank you. Doesn't matter where it's located, right? So if I look at the absolute value function, let's say this is shifted. The derivative, let's say it's shifted to the right 4 units. The derivative as I approach 4 from both sides, one side is -1, the other one's +1. Therefore, those derivatives don't agree, right? It might be continuous because both values, the limit as we approach from the left and the limit from the right, well, they're going to equal whatever this is. Let's say it's 2. But the slopes don't agree. So in this case, the slopes don't agree. What about another function that's continuous everywhere? A formal definition here and prove why, right? Here's your first principles or difference quotient. If the derivative from the left and the derivative from the right of that point that we're considering are not equal or don't agree, then it's not differentiable. So let's just confirm formally that this is continuous. Continuous at x equals 0. The only reason I want to do this is because you will be required to do this at some point. Do you remember what the first part of continuity is? If a function is continuous at 0, then what has to exist? F of 0 has to exist. Well, does it? Yes, it exists. Okay, so check. Number 1 done. Okay, so let's look at part 2, which is we have to have a limit from both sides of the function, and they have to equal the same value. They have to agree. Well, as I approach from the left, what's our limit? 0. As I approach from the right, what's our limit? 0. Therefore, they agree. Therefore, the third part of this formal definition of limits is f of c, or f of 0, agrees with the limit as x approaches 0. And do they? Yes, because 0 equals 0. So we're good. So we've proved that it's continuous. Let's prove that it is now not differentiable. It is not differentiable. So differentiable at x equals 0. Oops. And let's put a question mark there. Okay, so as we approach x from the left, what would be the derivative at 0 from the left side? Well, we know the function value from the left, so f of x, absolute value of x, is negative x when x is less than 0, and it's positive x when x is greater than or equal to 0. I could alternate the greater than or equal to or less than or equal to, doesn't matter. So as we approach from the left, this would equal negative 1. The derivative of negative x is negative 1. And the derivative as we approach 0 from the right, well, the derivative of x is positive 1, and because those don't agree, it's not differentiable. That's the formal process you have to go through in these problems. All right, so you're not going to have something as simple as this. It might be sine of x and, I don't know, let's say x cubed as x approaches 0. You'll have to consider the derivatives. What's the derivative of sine x? Cosine x. What's the derivative of x cubed? 3x squared. So if I want to test those, I do the cosine of 0. I do 3x squared, I plug in 0. Well, actually, excuse me, 3x squared, yep, that's the derivative, equals 0. Does 0 equal, no, they don't. They don't equal because the cosine of 0 equals 1. Therefore, that combination of functions, right, would not be differentiable at the point 0. That set of piecewise functions, I've got a slope of 0, I've got a slope of 1, therefore at that point doesn't work. Yeah. Easy way to remember that, hopefully. I'm going to take this, and I'm going to take the limit as h goes to 0 of, well, we're going to use sine x as our function. So if I plug that in, I get sine x plus h minus sine x, using the first principles here, over h. What can I do here to expand? Sports center, right? So I'm going to expand. This is formal. Now you know the answer to this. What is the answer to this? What's the derivative of sine x? Cosine x. Okay? This is our goal. We're going to come to that, but we have to do it the formal way first. So sports center, sine x, cosine h, plus or minus, plus sine h, cosine x. That was just this part. Minus sine x. You're going to have to do either this or cosine on the test, so it might be worth watching. Okay. Now I'm going to regroup some stuff. Let's take and regroup stuff that has a sine x in it. So I have sine x, cosine h, minus sine x. Okay, I'm just taking this term, grouping it with this term. And then I'm going to put that together here for a moment and add sine h cosine x. Oh, I see my friend over here. I'm waiting. I'm just waiting for the opportunity to isolate you. Yeah. Oh, okay. That was kind of creepy. Okay, cool. Yes, I was. That's great. I will get a very good review from the principals this year. Okay. Okay, so let's look at this. What do I have as a common factor in both of those terms? Sine x. If I take a sine x out, what does that leave me with? Cosine h minus 1. Okay, and over here I'm going to write sine of h cosine of x. Now, am I allowed to do this? Am I allowed to do that? Split the denominator between those two terms? Wouldn't this be true? 7 plus 11 halves would be 7 halves plus 11 halves. I could do that, right? Okay, now you might see what's happening here. Maybe. What's the limit of this as h goes to 0? 0. And what's the limit of this as h goes to 0? 1. So 0 times anything is 0, and 1 times cosine x is cosine x. So there is your derivative of sine x. It's cosine x. So anywhere along the sine curve, the slope at that given point is the y value of the cosine function at that x value. What? Yeah, for sure. Let's start here. What's the derivative of 5? 0, right? A constant has a derivative of 0. Okay, because if you think about a constant, it's a horizontal line, so it has a slope of 0. That makes sense. Let's take the derivative of x to the n. Correct. We take the exponent, we bring it down, and we take, and then we take the exponent and we subtract 1 from it. So example, and this one gets a lot of people, square root of x. One over 2 square root x, right? 1 over 2 root x. Because I take the exponent, right? I'm taking d dx, derivative with respect to x of x to the 1/2. Well, if I take that, bring it down in front, right, I get 1/2. But now the exponent of the variable is negative, so I got to bring that to the denominator, which becomes the square root of x in the denominator. All right, what else do we know? What's the derivative of, oh, your favorite? Yep, itself. That's the best function ever. What else? How about another exponential function? I think we talked about this last week. Close. It's the natural log of the base. Did I hear that or not? Times the function itself. Because if you think about this, isn't this just equal to the natural log of e times e to the x? Yeah, because the natural log of e is 1 anyways. So it follows the same deal, except this one's special. E to the x is special. All right, now I'm gonna mix it up. This is a favorite on exams. What is the derivative of the natural log of x? Yes, thank you. Okay, awesome. Good. That's awesome. Okay, good. Diogo. Each of these can be calculated or algebraically manipulated using the quotient rule. However, these need to be ones that you're just solid with. And maybe you're not there yet. That's okay. Tan x, derivative of tan x is secant squared x. Okay, derivative of cotangent. Think about this for a second. Cotangent and tangent are very similar. Not quite that easy. Okay, it's going to be negative cosecant squared x. So it's kind of like secant's buddy is cosecant. You know what I'm talking about? No? That's how I think of them. No. Secant x will be secant x tan x. And these can be proven using the quotient rule. We won't go into that right now. Anybody want to take a guess at cosecant? Negative. Hey, look at secant for a second. It had itself, right? So, cosecant. Not tangent, but cotangent x. Those are good derivatives to remember.